Okay, this is just the last part of the 6.3 notes. We left off on example 3, where we were looking at removing or eliminating the parameter. And to remove or eliminate the parameter, we said we need to solve for t and then substitute for t. So in this example, it doesn't matter which one you use, but the second one is probably a little bit easier. So if we have y equals 3t, solving for t, we divide by 3. T equals y over 3. Then we substitute that into our other equation, x equals y over 3 squared minus 2. We can leave it like that. That's sufficient. But if you don't know what that looks like, it might help to solve for y. So x equals y squared over 9 minus 2. X plus 2 equals y squared over 9. 9x plus 18 equals y squared. And then remembering our square root property, I can take the square root of both sides, but I need a plus or minus. Y equals plus or minus the square root of 9x plus 18. This is a sideways parabola. So we know that y equals x squared is an up and down parabola. X equals y squared is a sideways parabola. To find exact points, you can put this into your calculator either in function mode or in parameter mode. Since example 3 is the same equation from example 1, we already have the points from example 1 that we graphed earlier. However, this one is not going to end. This one will keep going because we did not have a limit on t. On the next page, example 4, we're doing the same thing, except this time our parameters are in terms of sine and cosine. And anytime we have our parameters in terms of sine and cosine, the most straightforward way to substitute for t is to use the Pythagorean identity number 1. So we're going to use sine squared t plus cosine squared t equals 1. That means I'd like to solve for sine and cosine. So for here, to solve for cosine, divide both sides by 2. Cosine is x over 2. For my second equation, I can solve for sine. Sine is y over 2. I'm going to go ahead and substitute that into the Pythagorean identity. Sine squared plus cosine squared is 1. Sine is y over 2, so that becomes y over 2 squared. Cosine is x over 2, so that becomes x over 2 squared equals 1. This becomes y squared over 4 plus x squared over 4 equals 1. And then if we multiply everything through by 4, we actually end up with, I'm going to write it x squared plus y squared equals 4. Now, this type of equation is important because this is actually the equation of a circle. This equation of a circle, x squared plus y squared equals r squared. So we know that this circle has a radius of 2. So when we graph this, and you can scale your graph if you'd like to draw it bigger, but we end up with a circle with a radius of 2. The last topic that we're going to look at is parameterizing lines and line segments. And to do that, we're going to use vectors. A vector has a starting point and then a direction. And so with that in mind, we can parameterize a line by starting at point A, for example, and then saying that all points that are multiples of my vector give me points on this line. So what that looks like is starting from directions from O to A, we would get the vector -2, 3. And then we're going to add all of these little vectors, which are all multiples going in either direction of vector AB. So we're going to say all of the multiples of vector AB. So in order to find vector AB, we're going to have to do some subtraction. So we're going to say the multiples of, and then the vector AB is going to be the difference of x's and the difference of y's in component form. 3 minus -2, comma 6 minus 3, which is how we found a vector from 2 points. And then from there, we're just going to go ahead and solve. And that's going to give us a parametrization of the whole line, line AB. So we continue to solve. 5, comma 3. And then distributing, quote unquote, distributing that t. 5t, 3t. And then to add my vectors, I add component-wise. So that's -2 plus 5t and 3 plus 3t. And this will give us a parametrization of the line, which means this is my x and this is my y. So we end up with x equals 5t minus 2, y equals 3t plus 3. I put them into slope-intercept form just because that's the way that we are used to seeing our equations. Okay, that is not the only parametrization of the line. There are an infinite number of ways to write the parametrization of this line, but that's the most straightforward way to find it. Now that represents the entire line because I didn't restrict my t values. I can get any point along this line. So if I wanted to find a line segment with n points, then I do the same process, but I limit my values for t. So in example 6, we have the same points. So we have the same parametrization. But if we want endpoints, then we need to limit our t values. And so in order to do that, what we're going to do is we're going to calculate what t values give us the point at A and the point at B, which are now our endpoints. Well, remember we started at point A and we added a vector. Well, if we don't want to go past point A, then we don't want to add any vector. So that's going to be 0. So we're going to start at t equals 0. And then if we add all of these vectors, this is 0.1 times vector AB, 0.2 times vector AB, all the way up to vector AB is going to be when t is 1. A way you can double check this is you can substitute in values of t and check your x and y values. So this parameter would limit itself between 0 and 1. This would be point A, this would be point B. Okay, that's the end of our notes section. Now you're going to go ahead and work on the Desmos, and anything you don't finish is for homework.